this video, we are going for the derivation of the equivalent resistance of this parallel combination of two resistors. Here you have two resistors connected parallel like this. So this is what the single resistor defined as the equivalent resistance of this combination. So the principle of equivalence indicates that when this combination is replaced with this single resistor, that replacement makes no difference in the current and in the voltage of this combination. Simply, this replacement is made possible if it makes no difference in the original circuit. So the mathematical relation about this equivalency can be obtained like this way. You think when this current I passing through the combination creates a voltage across the combination V. When the same current is sent through its equivalent one, the same voltage has to be generated across that. Now you can see here the current are same, the voltages are same. Then this can be replaced by the single one. If this is possible, now we call these two are equivalent. So from the principle of equivalency, actually this principle of equivalence indicates that the current I passing through the combination creates the voltage V. The same voltage will be created when the same current passing through its equivalent one. Now consider here, this current comes into the combination and it splits into two parts. The I1 going through the R1 and the rest of the current going through the other path, say through R2 here. The current going through R1 creates a voltage across that and it comes like this. This current going through R2 creates a voltage across R2. This current eventually comes like this. So by combining these two currents, the same current I will be generated and coming into the point B like this. So look at this junction. This current coming into the junction has to be equal to the total current coming out of this junction, because there is no possibility in accumulating the charges at the junction as well as in creating the charges at the junction. Therefore charge flow has to be conserved. This total charge coming into the junction equals the total charge coming out of the junction in 1 second. So with this principle, that principle is called actually the Kirchhoff law. So from this principle we can write this I as the current I1 plus I2 here. This I is what this total current coming into the junction, which is equal to this total charge coming out of the junction, that is I1 plus I2. Now we can write this I1, I2 and I values assuming these resistors obey Ohm's law as well as assuming this principle of equivalency. Now we can write this I regarding the equivalent resistor. This I is V by this resistor. So this I is written as the voltage across the equivalent resistor divided by the resistance here equals I1 is the current going through the resistor R1, creating the same voltage V. The resistance is R1 equals I2 is the current going through the R2. Therefore voltage across R2 is equal, that is common voltage, by its resistance, that is R2. Now you can look at this combination. This one terminals of the resistors common, the other one is common to that point. Therefore the voltage across both R1 and R2 are same. Now you can simplify this common voltage term, cancelling it out and becoming this equation into the form, say 1 by R equivalent. This is the equivalent resistance. So here 1 by R1, one of the resistances in the combination, plus the other resistance of the combination 1 by R2. So this is the most popular way of stating this relation in general. So for the special situation where only two resistors are present, we can get that more simplified into the form, say 1 by R is written like this, 1 by R is written like this, one by R equivalent, and you can write the product here, R1 times R2 here, upside you have here R2 plus here you have R1. This is the sum of the resistances and the product of the resistances. So by flipping this you can get the subject Req as the product of the resistances R1 times R2 here up the sum of the resistances R1 plus R2 down. So this is the one of the most applicable equation straight away when doing MCQs. So let's consider a special situation where the n number of identical resistances are in parallel combination. So when n number of resistances are in parallel combination, how to find the equivalent resistance of that combination? Now we can go for that consideration. When n number of resistors each having the resistance capital R are in parallel combination. How to find the equivalent resistance? The equivalent resistance can be found as like this. Look at the expression. Now we go for the first equation that indicates the 1 by R equivalent equals, so 1 by R plus 1 by r plus 1 by r. Here you have the n times of the 1 by r term in the right side. So the 1 by r can be taken out. So inside bracket you have 1 plus 1 plus 1 plus 1 plus and so forth. The how many times of the 1? Then n. Then n times of 1 is n. Therefore, by flipping this, you can get Req as R by n. You can just divide this one resistance by the number of resistors in the parallel combination. So this is most useful way when doing the complex circuit analysis in the physics problems. As an example, if there are two resistors each having the resistance R in the parallel combination, the equivalent one is R by 2. When having 3 resistors, then R by 3. When having 4 resistors, R by 4, like that. Now look at the previous step, that is step here. What does this principle indicate? That indicate the current at the junction are additive. So the voltage across this equals that across that. So we can indicate these conceptual principles regarding this parallel combination of resistors. So for the parallel combination of resistors, the first one, the voltage is constant. Voltage is constant. The second one, the currents are additive. So these are the two conditions with which a parallel combination of resistors is identified. Thank you very much.